In this lesson, we introduce the notion of transforming variables in a regression model and introduce the most popular transformation, the natural log transformation of variables. We understand why we may want to transform variables and introduce two popular transformations, the log-log transformation and the semi-log transformation. We will introduce a common transformation of variables used in regression modeling, namely the natural log transformation. But before that, let us understand why we would want to transform variables in a regression. Recollect that regression is a linear procedure, that is, it fits a straight line through the data. It establishes a linear relationship between the y and x variables. What happens if the actual relationship between the y and x variable is not linear? For example, if we are wanting to estimate a simple model as shown, y is equal to beta 0 plus beta 1 times x, this model has a single explanatory variable. So, we collect data on y and x variables and a scatter plot of this data is as shown. The scatter plot visually shows us the relationship between y and x variable. Clearly, this is not a linear relationship. There is a distinct curvature or non-linearity in the plot. If we fit a regression model to this data, the model will provide us with the best fitting straight line as shown. However, even the best fitting straight line is not a good representation of the relationship between y and x variables. This would result in poor R square measures and poor prediction and interpretation from the model. One option to deal with this is to invest our time and effort to learn some non-linear regression techniques. However, that may require considerable effort. The other option is to try and do some transformation in the data in the hope that the relationship becomes a little more linear. The more linear the relationship becomes, the better would a regression model fit the data. This would then further result in improved R square measures. The transformations that you could use are many. For example, you could invert one of the variable or both variables. You could take the square of a variable, a square root of a variable, and so on. It requires a bit of trial and error. The most common transformation, though, is the natural log transformation. You could take the natural log of your y variable as well as the x variable. The natural log transformation is popular enough that we have names for regression models using these transformations, the log-log model and the semi-log model. However, before we introduce these models, we need to recap some basic properties of the natural log function. They are shown in the visual, and it may be a good idea for you all to review them and come up to speed with the basic natural log properties. The function in Excel to calculate natural log is the is equal to ln function. Coming back to the regression models, in a log-log model, you take the natural log of the y variable as well as the x variable, while in the semi-log model you log transform your y variable, but not the x variable. To interpret the coefficients in a log-log or semi-log model, you can take the same approach as earlier. For example, in the log-log model, the coefficient beta 1 is interpreted as shown. When the natural log of x 1 increases by 1 unit, then the natural log of y increases by beta 1 units, all other variables remaining at the same level. Now, pause for a moment and think about this interpretation. There is nothing wrong in the interpretation. However, it is difficult to understand. Imagine the toy sales regression model from earlier lessons in a log-log form as shown. Let us say you estimate this model and get the estimates as shown. The estimate of beta 3 is positive 1.43, and you now wish to convey to your boss the impact of promotion expenditure on sales. It may be difficult to understand for your boss if you tell him or her that if the company increases the natural log of promotion expenditures by 1 unit, then the natural log of unit sales of the toy will increase by 1.43 units, all other variables remaining at the same level. There is nothing wrong in this interpretation, just that it is difficult to make sense of and act upon. However, if you do some math on this interpretation, the math part we will skip, this very interpretation transforms to as shown. If the promotion expenditure increases by 1%, then the unit sales will increase by 1.43%, all other variables remaining at the same level. Notice that the interpretation is in terms of percentages and not units. Further, it does not involve log in the interpretation. This interpretation is certainly more easy to understand and act upon. So, that brings us to the general interpretation in a log-log model, which is as shown. 1% increase in x1 corresponds to a beta 1% increase in y, all other variables remaining at the same level. Other coefficients are interpreted similarly. Note that this interpretation by definition is also the elasticity interpretation. So, beta 1 can also be interpreted as the elasticity of y with respect to x1 and so on. Some maths on the interpretations in the semi-log model lead to the approximate interpretation as shown. 1 unit increase in x1 corresponds to a 100 times beta 1% increase in y. Notice the difference in interpretations here. x1 increases by 1 unit, not 1%, and y increases by 100 times beta 1% and not beta 1%. In the next lesson, we will continue our study of these models.